Welcome everyone for this one last session of the cryptography course in our EPF study group. So it's been 2 months since the study group started. It's been quite a ride. Last 6 weeks actually, we've been having these two tracks of lean and cryptography, and today is the ultimate one last session on the cryptography of Ethereum. Finally getting to those curves. I hope you guys are ready, and please, this is the last opportunity to ask questions and discuss details with Matan. So if you're unsure of anything, if you want to chat about some details, if you have any questions, please use the opportunity now to bring up any insights, any questions. And yeah, let's kick it off. It will be lecture 5. Yeah.
Okay, thanks Mario, and welcome back. As promised, we will cover elliptic curves today, and I want to start with the actual cryptographic motivation. So this is the lecture is aimed to get into BLS signatures. And BLS is acronym for Bonnet, Lean, and Shacham. And this is a type of signature that is better than the RSA signature that we saw last time, in the sense that it's very, very efficient in aggregating basically any number of signatures. So you can imagine why it's a much better signature scheme for large scales. And the premise of the signature relies on some mathematical structure that I will at the moment assume, and later on we will unravel and see how to construct it. So suppose we have 3 prime order groups that I will denote as G1, maybe, yeah, prime order cyclic groups. In fact, any prime order group is automatically cyclic, but we can just assume this in addition. So G1 is going to be written additively. It's G1 with plus and 0. G2 is also written additively. And GT is written multiplicatively. And again, the construction we will do later on will explain why this is the case, or why these notations are chosen. And we said that these are cyclic groups. So let's say G1 is generated by a generator G1, the same for G2. And a GT, we don't need really a generator, but just in case, GT. And furthermore, I assume that a discrete log is hard in each. Okay, so that's the groups, and if we further assume we have a pairing. A pairing is just a map E from G1 times G2 into GT, such that three properties. So the first property is bilinearity. And this means that for any A and B in Z, of course I can write AX as the abbreviate notation for X plus X plus X A times. If A is negative, then this is minus X plus the sum of minus X with itself A times. So for any A and B, bilinearity says that if you do E of A P and BQ, where P is in G1 and Q is in G2. Then what you get is exactly E of P and Q to the power of A times B. The second property is non-degeneracy. And this means that if P and Q are not the zero element in their respective group, then E of P and Q is not the neutral element in the target group, GT. And three, this is kind of always we want to assume, is that E is efficiently computable. Okay, and so I hear myself in echo, I think. Okay, so we want E to be efficiently computable and one way, i.e. From EPQ, hard to recover P and Q. Okay. Guess I'm still hearing myself in an echo. Let me try to. Okay, maybe it's better now. Yeah, so these are the assumptions, okay? And now we construct the scheme. So fix a hash function h from 0, 1 star into G1. If you want, I mean, this, we talked about hash functions. You are used to hash functions that take a bit string. This is the set of bit strings. and give you a limited length bit string, let's say a 256 bit string. And to get a hash function into a group, well, I mean, you can assume, for example, that the order of G1, which is prime, is some 256-bit prime, and then you can identify the landscape of, I mean, the set of 256-bit sequences with the elements of G1. So once you chose some identification, you get a hash function into G1 instead of into bit strings of length 256. And now the BLS scheme, as all schemes, it has a key generation, and that is the signer. It chooses a secret key out of, so let's say, for convenience, let's say the G1 and G2 and GT are of size R. Okay. So I have three groups of the same prime order, R, and now I need to generate a secret key. So I asked the signer to take uniformly at random an element out of integers modulo R. And the signer generates a public key. The public key is S times age of the message. Is, sorry, apologize. The public key is SG2. SG2, again, I remind you, it's like it just, this bracket is kind of a notation to say G2 plus G2 plus G2 S times. Okay, so this is the signer, and now the signer takes a message for some message M, which is a bit string. The signer computes sigma, which is S, of age of M, age of the message. And remember, age, it falls into G1. So the signature sigma is an element of G1. Okay, so what we have the public key is an element of G2, and the signature is an element of G1. And now somebody needs to verify. So the verifier, what does they have? What do they have? They have all the public information. So they have G2 and the generator of G2. And they have G1 and the generator of G1. And also GT. And they check. So they get a message and the signature attached to this message, signed by the signer. and they need to verify that this is indeed a valid signature. So they get and check against the public key, which is again public, that E of sigma G2 is equal to E of age of M G2, E of age of M public key. And except if and only if the equality holds. Now, why is this a verification sound? I mean, correct, let's say. So correctness. This is exactly the property of bilinearity. So I take E, let's say somebody was an honest signer. They have a public key SG2, so the secret key is S, and they signed a message using this, and I take their signature, and I have G2, but their signature is S HM, if they were honest, G2. And by the bilinearity, this is the same as E of HM G2 to the power of S. Because remember, this guy lives in GT, which is a multiplicative group. So this is bilinearity. And also by bilinearity in the second argument, this has to be equal to E of HM. And now, because I have an additive group, I write SG2. But SG2 is by definition the public key. I mean, if the signer was honest. So indeed, I get E of HM public key. So HM, I calculate myself. So the verifier gets sigma and M, computes age of M. So implicitly what this says is that age must be public, or at least available to the verifier. And you see that by the properties of bilinearity, I get a signature. So far, questions about this scheme? I want to show aggregation, but I don't want to rush it. Okay. Yes, okay. So, so no questions so far, I see. What is the nice property? I mean, suppose I people sign, well, not I, maybe N people sign N messages. So I have a message I have the signature on message I. For the I person, I have this tuple, sigma I mi. And again, I'm assuming everyone is honest. So sigma I is somebody took their secret key, SI, and multiplied it with age of MI. And this lives, again, sigma always lives in G1. Okay, so now I get all my, I'm a verifier, and I get all the signatures, and I define the aggregated signature to be simply the sum of all these signatures. This is all these signatures, they live in G1, and I have a sum in G1, so I take simply the sum. This is explicitly, it's just SI, age of MI, where I runs from 1 to n. And now I don't want, I mean, n could be very large. So, and I want to know, whether everyone had a valid signature or not. I don't, if somebody failed, it's everything is failed for me. But can I check it in an aggregated way? So I propose to check that E of the aggregated signature with G2 is equal to the product I equals 1 to n of E of the hash of the I message with the public key of the I guy. And again, I accept if and only if I have equality, and I reject otherwise. Correctness. So assuming everyone is honest, again, I have E of sigma aggregated paired with G2. G2, the generator of the group big G2. This is by definition E of the sum of all the sigma i's with G2. But some here, some in each of the variables can get out as a product. This is a bilinearity. So I get pi of E of sigma I G2, where I runs from 1 to n. Okay, this is pi of E of Si age Mi G2, which if I go one by one, I can replace, because the signature works for one guy, I can replace each component of the product by E of age Mi S G2, which is the public key. So this is pi of E of age Mi PKI. Okay, so if assuming all the signers were honest, I get correctness of this aggregated signature, and I did only one calculation. I basically, I just needed to verify one equation. I paired this sigma aggregated with G2, and I needed to check that that it gives me another pair. So what did I need to do? I needed to aggregate all the signatures. This is like addition in G2 is like maybe addition in some prime field, maybe slightly more expensive. And then I need to calculate two pairings. So I need to do n additions and to calculate two pairings, and I basically verified the aggregated signature. Okay, so this is super efficient, and it is well for what is called non-post-quantum secure cryptographic primitives. This is as good as it gets. I mean, you can aggregate with almost no overhead any number of signatures and verify them. Well, the verification is really in constant time. It doesn't depend on the number of signatures. So this is BLS. Any questions on BLS?
Yeah, Lee has a question, I think. Yeah.
Yes. I'm wondering why can we simply move the sum out of the pairing and make it the product? I don't see we have the definition before, right?
Yeah, I guess this is a little bit of a leap. When I said bilinearity, an equivalent way of saying bilinearity is that, let me write it. It's maybe not immediately clear. For any P and Q, or let's say P prime, Q prime, if I do E of P plus P prime, and I pair it with Q, it's the same as doing E of P paired with Q, multiplied by E of P prime paired with Q. And the same for the second variable, E of P Q plus Q prime is equal to E of PQ times E of PQ prime. Or equivalently, and I mean, this is a small exercise to see that these are two definitions are equivalent, that for any A and B, you get this property. Okay? Is this answering your question, Lee?
Yeah, that's clear. And one more question, just in this zone, we define we have the feature like a non-degeneracy, and I assume that's for the safety consideration. But can you give a counterexample? Say if there exists as a E applied to P and Q equals to 1, what will happen?
Well, I mean, because P and Q live in a cyclic group, this would collapse and everything, right? Because P is just, I mean, is just some K times the generator, right? So suppose you had just 2 points, P and Q, that are not zero, and whose pairing is equal to 1. Then I write P as K times the generator, right? And Q as L times the, let's say P is in G1, so let's say K times the generator of G1, and Q is L times the generator of G2. Then I will have E, let me write it in yellow, E of K G1, L G2. This is E of G1 G2 to the K times L. But this is equal to 1, right? And and this means that E of G1, G2 would also be equal to 1. So and by easy induction, E of everything is going to be equal to 1. Okay? Lee, is this clear? Maybe it's a little bit fuzzy, but the short answer is that everything is collapsing in this case.
I'm now. I know. I mean, I don't. Yes, I understand. Like, E, G1 and G2 power to the K times L will be collapsed to 1, but it's still 1 point, right? It doesn't implies E, G1, G2 actually will equal to 1. That's different, right?
Yes, I know. I didn't specify a proof, but it will be this way. What will happen is that E of G1, G2 is going to be equal to 1, and therefore E of everything is going to be equal to 1.
Okay, cool. Do we need to prove like, do you need to prove, I mean, like, should we need to prove like K times L actually is not the like what's that term? It's like the one will exponent will cancel the like will cancel everything to 1.
No, it cannot. Look, the exponent cannot cancel everything because
Yeah.
E of G1, G2 is an element of GT, okay? Here
Yeah.
in green. And GT is a group of prime order. So unless K and L are equal to R, K times L is equal to R, to the order of GT, then E of G1, NE of G1, G2 is not 1, then you can never get E of G1, G2 to the power of KL equal to 1. Never, because in order for an element in a group of prime, in any group, to have a power equals to 1, it means that his power needs to divide the order of the group. So this is why I'm saying it's okay. There is a small proof to unravel, but the bottom line is that if you don't assume non-degeneracy, then everything collapses. Everything, the pairing of any 2 points is going to be 1.
Okay, thanks a lot.
Okay, so you see, once we had a pairing with these beautiful properties of bilinearity, essentially, then we could do a very good cryptographic improvement. And this is supposed to be a motivation for the rest of this talk, because these G1, G2, and GT come from elliptic curves. Which I will abbreviate as EC. So what is an elliptic curve? These groups, of course, with the pairing. Okay, so definition. Let F be a field. And let's assume that the characteristic of F is not a 2 or 3. That's okay, because usually we take a very large prime as the characteristic. An elliptic curve defined over F is an equation let me write it like this. E equals EAB And the equation is y squared equals x cubed plus ax plus b, where a and b are elements in F, such that there is a small condition that what is called the discriminant of E, which is 4a cubed plus 27b squared, I believe, yeah, is not equal to 0. Now, why do I say equation? And the notation here, is E over FP. So to say that an elliptic curve, you have an elliptic curve over a field, sorry, this over F. Elliptic curve over a field F, it simply means that you have an equation of this form such that the coefficients A and B are in the field. Now this guy is called S of X, and we say that the rational F points of E is the set E of F. It's the set of all pairs x comma y in F square, such that the equation holds, right? So y square equals x cubed plus ax plus b. But I need to add one more thing. So I add a point which I call O, and you can think of it intuitively as infinity comma infinity. It's like if you substitute instead of x infinity, then you get another solution where y is equal to infinity. So infinity comma infinity is also kind of a solution to this equation. This is called the point at infinity. And these guys are called the finite points. So finite simply means that they are not the point at infinity, and the notation here is E of F finite. Okay, so that's an elliptic curve. And let's do an example. Take F equals R. Then the rough picture of an elliptic curve, I mean the points, the finite points of an elliptic curve over R are something like a fish. Okay, where it should be symmetric along the x-axis. And this point, let's say I, it has xi and yi, but yi is equal to 0, right? This is the y-axis. This is the x-axis. So it means that xi is a root of this polynomial s that appear in the right-hand side of the equation of an elliptic curve. Okay. So this over R is it's a very nice picture. And because it is symmetric, so if I take P to be a point over the elliptic curve over the real numbers, for example. So let's say P is somewhere here. Then I define, at the moment it's just a notation, minus P. So let's say P is XP, YP. I define minus P to be the reflection along the x-axis of P. So this is XP, comma, minus YP. But you see that what I did here, I mean, I can do for over any field. I can simply put a minus over the y coordinate of a point over any field. And what do I have here? I have this curve, and I want to define some kind of group law. So the group law is as follows. Maybe I can do a better drawing. Suppose you took 2 points, let's say P here and Q here. You can take the line that connects P and Q. Again, this is over the real numbers, but as we saw previously, lines make sense over any field, right? It's just a linear equation. It's the solution of some linear equation. Now, because this is a curve of degree 3, this y squared equals x cubed plus ax plus b, then I am guaranteed that there is exactly 1 point in addition that this line intersects the curve. So this is E, right? And the green line intersects E in an additional point, which I call R. And I define P plus Q to be minus R, the reflection of R along the x-axis. Now, there are some edge cases, okay? So 2 edge cases. First, what happens if I want to add a point to itself? So let's say I want to add a point P to itself. So I connect, I draw the one line that is tangent to the curve at P. Say like this. And this line, the tangent line at P, will intersect, again, because this is a curve of degree 3, it will intersect the curve at one additional point, R. And I define P plus P to be minus R. Okay, the reflection of R along the x-axis. And then finally, I have the case of this tipping point of the curve, which we called I before. And I mean, again, let's say I want to add I to itself, then I get a tangent line that does not intersect the curve anymore. But because I have this point at infinity, which is like somewhere here, but also somewhere here, just intuitively, I mean, formally speaking, I say that I plus I is equal to O, which means, of course, that I is equal to minus I. And that's it. And I say, let's say here, for any P, I define P plus O to be P. So I needed O as a neutral element. I don't have a neutral element if I just do this geometric construction without a point at infinity. And the main theorem, this is not an easy thing to prove, but this makes the rational points E of F into an abelian group. Okay, with O as a neutral element. So this is kind of a magic because I did some geometric construction. What is, I mean, the sort of magic is that it's not clear at all why this construction is going to be associative. Okay, it's not clear why if I have P, Q, and L, then P plus Q, as I defined here, plus L is the same as P plus Q plus L. Okay. But it is questions about the definition. How do we multiply in GT? I didn't say yet. GT is going to be, I didn't say what is G1, G2, and GT. G1 and G2 are going to be coming from an elliptic curve, and a GT is going to come from a field. So it's going to be the multiplication in the field. Other questions about this definition and the group law of an elliptic curve? Now, what you need to understand is that what I did here geometrically makes sense over any field. Why? Because the line that passes through P and Q is just an equation. I mean, L of PQ, let's say P is XP, YP, and Q is the same. Then the line of P and Q, the line between P and Q, you calculate first the slope, M. M is going to be, let's say, YP minus YQ. Sorry, YP minus, yes, YP minus YQ divided by XP minus XQ. And then Y minus YP equals M times X minus XP is the equation of the line between P and Q. Okay? And now, in order to find R is some XR, YR, you have this equation. I mean, R needs to satisfy YR minus YP equals M XR minus XP. But you also know that R needs to be on the curve. So you know that YR square, it has to be equal to XR square, sorry, XR cube plus AX plus AXR plus B. So you have two equations in two variables, and there is a canonical way to solve this system of equations and to get a unique point R. Yes, question.
Yes. Actually, it's a question from previous previous part. So we say the character of the field cannot be 2 and 3. I'm wondering why.
It's not just, I mean, this equation that I wrote, this is called a short Weierstrass form. You can define elliptic curves over a field of characteristic 2 and 3, but then the equation is a bit more complicated. And I wanted to simplify. So this form of what is called the short Weierstrass form, in my opinion, it's much more simpler, and it is only valid in characteristic different than 2 and 3. But again, for us, it doesn't matter because we're going to work over a field of very large prime characteristic.
Okay, cool. Thank
Okay, so you see, I can this over any f. Let's say what you should have in mind is like f equals fp. I have the notion of a line. I mean, the line of P and Q is simply the collection of all points x, y, such that y minus y, yp is equal to m times x minus xp. Okay, so it's just a collection of solutions of points to this equation. And the same goes for a tangent line. A tangent line I can do, so this requires a little bit of calculus if you want to understand the general case. So a tangent line, it's going to be a similar equation for P not equal to I. I take M to be dy to dx evaluated at P. And then the tangent line at P is going to be an equation exactly of this form, y minus yp equals m x minus xp. So m is like the slope of the line. If you remember from calculus, the slope of the line is like the derivative of the function at this point. So you see this guy, for example, here this guy has some m, the yellow line has some m. M is going to be dy to dx evaluated at P. And we will do a precise example after the break. But you see, dy to dx, I mean, I'm dealing with polynomials. I don't have any sines or crazy functions. Polynomials, I can derive formally. I mean, let's say in the general case, I have y squared equals x cubed plus ax plus b. I do a derivation. So I think of y as equal to y to a function of x. It's not exactly the case because I have y squared, so it's like two functions. So I do what is called implicit derivation, but I just do it formally as polynomials. So this is like 2y dy is equal to 3x squared plus a dx. Okay, and this means that dy to dx, I don't have I don't have a complete X expression for this because this is not a function, but I have, this is 2y divided by 3x squared plus a. So now dy to dx at p is, 2yp divided by 3xp squared plus a. So you check whether this guy, I mean, this is going to be equal to your slope, and you construct the tangent line here in green, again over any field. What I did here, it does not depend on the real numbers. It's just that the geometric intuition of how to interpret this law in a shape on the xy axis, this is only valid for over the real numbers. But the equations themselves, they are valid over any field. What I explained is that the line between P and Q on the curve and the tangent line at P relative to the curve are things that have a meaning over any field because they are just equations. And what I like to warn you here is that, let's say, over a finite field Fp, the Fp points over a curve do not have any meaningful shape. I mean, because one common mistake is people saying, okay, I know the shape of an elliptic curve over the real numbers is kind of this fish. So let's suppose I have a large prime, so I can order the elements of the prime field like this, and the same on the y-axis, and I will get some kind of I don't know, some kind of shape similar to what I had before. But this is very, very wrong, because remember that the arithmetic that we have over Fp is not addition and multiplication of the integers. It's addition and multiplication modulo p. So things that are equal without modulo p can be non-equal. I mean, things that are equal modulo p will stay equal. Things that are equal not modulo p will stay equal not modulo p. But you will have many other things that come because of the modulo p arithmetic. So the elliptic curve over Fp is going to be a scattered collection of points that have no meaningful geometry or not meaningful shape, but it has a geometry in the analogy case or in the analogy sense, because again we have a notion of a line. A line is just an equation like in the green, for example. We have a notion of a tangent line. We have a notion of a derivation, so we can define the tangent line. We can define the line between P and Q on the curve, and these lines, okay, they are a collection of points, but they don't have to align. I mean, a line could be the collection of these yellow points, for example, this point and this point and this point. This could be a line over Fp, okay? A last remark before we leave the kind of theory land. The condition that a delta E, the discriminant of E, which is 4A cube plus 27B squared, is not equal to 0, is equivalent to say that every P in EF admits a tangent line, admits a well-defined tangent line. That is given by this dy to dx at P. I mean, if you think of a dy to dx, the way we wrote it, it's a quotient of thing, and so sometimes it can get to, I mean, it can become infinity. And then what is the slope of the tangent? I want to allow only a tangent line with a slope equal to infinity, only in the case where I have some a parallel line to the y-axis, and all the rest of them need to have a well-defined tangent line. An example of something that is I mean has this shape, let's say y squared equals x cubed. This is the discriminant here is 0. And the way the curve looks like is kind of an alpha shape. And you see that I don't have a well-defined tangent line at 0, because on one hand, I would want the tangent line to be this yellow line, but it could also be this yellow line. So I cannot decide. I don't have a well-defined tangent line. But the condition on the elliptic curve is that every point admits a tangent line. And so on every point, I can do the point plus itself. Because the point plus itself is you draw the tangent line at the point, you take the intersection with the curve, you reflect along the x-axis, and that's the result. This is called, by the way, doubling P, because P plus P is, in our notation, this is 2P. Okay, so let's do an example. I take, well, what did I take? I take E to be the following curve: y squared equals x cubed plus x plus 1 over f5. So this is a toy example, okay? I mean, in practice, people work over a very, very large prime fields, but we cannot do calculation like this. So we take a toy example. The discriminant, just to verify that this is indeed has a tangent line at every point, what is called a smooth curve. This is 4 plus 27 modulo 5 is different than 0. Okay, and now I take 2 points. P is going to be 0, 1, and Q is going to be 2, 1. Both points are in F5 squared, but I claim they live on the rational points, the F5 rational points on E. Well, what do you need to see? I mean, so this is XP, this is YP. I need to verify that 1 squared is equal to, well, 0 cubed plus 0 plus 1, and this is okay. So P is on the curve. Q, I will verify that 1 square is equal to 2 cube plus 2 plus 1 modulo 5. And this is also true because this is 8, plus 2 is 10, plus 1 is 11, modulo 5 is 1. Okay, what is the line between P and Q? I need to calculate this line in order to calculate P plus Q. So the line is of course, like any line, is y equals, we call it M. M, let's say x minus xp plus yp. This is the line between P and Q, where M is yq minus yp divided by xq minus xp. And if you do the calculation, you get that this is 0. So the line is actually y equals 1. Okay, this is like a tangent line. I mean, this is not a tangent. This is a line parallel to the x-axis, which is usually not the. Okay, so this is the line we have, and now we need to find the intersection. Intersection with E. So I substitute y equals 1. This is, so R is xr yr, but clearly, since R needs to be on the line, yr needs to be equal to 1. So xr is going to be the solution of this following cubic. And over F5, remember, we are over F5, the solutions are 0, 2, and 3. But 0 and 2 are already appearing in P and Q. Remember, P is 0, 1, and Q is 2, 1. So XR has to be the third point. So R is equal to 3, 1, and P plus Q is the reflection of R along the x-axis. This is simply 3, minus 1. But again, what is minus 1 in F5? Minus 1 in F5 is 4. So this is 3, 4. Okay? This is how you calculate the addition of 2 points. Now you say, okay, if I'm going to build a cryptography on this thing, I will need to calculate addition of points, and this is going to cost me, right? I need to solve equations all the time. It's not just like, and then in addition, I will need to do the modulus in the prime field. So this is much more expensive than just adding 2 elements in the prime field. However, it's also much more expensive for an attacker to solve the discrete log. So what I get here, the hardness assumption, I mean, discrete log in a elliptic curve group, it's basically subgroup, is hard. But the real issue is, what is the relation between the hardness of adding points, let's say doing the arithmetic in the group of the elliptic curve, and the size of the prime such that the hardness assumption, the discrete log in the group will be hard for an attacker. So I'm making myself, my life harder in terms of arithmetic in the group, but I can maybe, and this, it turns out that I can choose a much smaller prime than the usual prime that we chose in, if you remember, in Diffie-Hellman, we chose a prime group of order 2000 bits. And here it's enough to get a prime, I mean, an elliptic curve over a prime field of 300 bits. In order to get the same level of security, what is, let's say, 128 bits of security, you work with much smaller prime. So the operations in the group are maybe expensive, but the prime itself, in order to get the same bits of security, I can work with a smaller prime. And at the end of the day, and these people understood years ago, it turns out that it's more efficient to work with an elliptic curve group even for the Diffie-Hellman protocol. And so most of the cryptography you see, even if it's not using pairings, it's using elliptic curve groups for efficiency. Okay, next thing, we did an example. Observe. If E is defined over Fp and K is bigger than 1, then, I mean, what is E defined over Fp? This is EAB, right? EAB means a y square equals x cubed plus ax plus b, with A and B living in Fp. I can speak about the points of E over some extension of the original prime field. What is it? Well, it's the same. It's like the x comma y, but now they live in the extension. So Fp to the k times Fp to the k, such that y square is equal to x cubed plus ax plus b. I mean, A and B are elements in Fp, but Fp is contained, is a subfield of Fp to the k. So if A and B are here, I can also think about them here. And this equation means, I mean, is still meaningful. And of course, I add the point at infinity. So by that, I get that EFP, the Fp points on E, is a subgroup of the Fp to the k points over E. And this is why it is useful to think about E, I mean, about an elliptic curve, as just an equation defined over some base field. But the group itself, you have many groups. You have an infinite ladder of groups, I mean, when you take extension of the field. And each of them is a useful group in its own. And they are subgroups of each other. And so one elliptic curve defines many groups. Okay. How many points do I have on an elliptic curve? Approximately. This is called the Hasse-Weil bound. It says that for an elliptic curve over some field FQ, the number of points of E over FQ is bounded below by Q plus 1 minus 2 square Q, and bounded above by Q plus 1 plus 2 square of Q. And this really means, to simplify, it means that the number of points of E over FQ is approximately Q. Okay, so if you choose a large field, you are guaranteed to get a large group. Torsion. So let E over FP be an elliptic curve, and K some integer bigger than 1, bigger or equal to 1. An N torsion point of E over Fp to the K is a point P in the Fp to the K rational points, such that Np, which I remind you is P plus itself N times, is equal to O. Okay, this is all the points that if you that are nullified by multiplication with the integer n. Now observe, this is denoted E F P to the K, and then brackets n. Okay, this brackets n means the n torsion points. And observe E F P to the K n is a group, is a subgroup of E F P to the K. Why? I mean, take 2 points, P and Q, that are n torsion points in EFP to the K. Then, now I need to check that if I multiply them by n, I get 0. But by arithmetics, this is n P plus n Q. And P and Q, I started with torsion points. So each of them is nullified by n, and I get nullified by P and Q. And similarly, if you try to multiply minus P by n, this is the same as minus of NP. This is minus O, which is O. Okay, so this is the group. I'm going to take well, okay. Before I go to that, maybe it's better to state a theorem. Let's call it theorem X. theorem star. Suppose E over FP an elliptic curve, and R is a prime dividing the order of the group. The order of the group is usually not prime. But it has a prime factor. And suppose I take K, the smallest integer, is such that R divides P to the K minus 1. Okay, this I can do with any curve. If K is bigger than 1, which is the same as saying that R does not divide P minus 1, then I have two major statements. One is that the R torsion points of E over FP are isomorphic to integers modulo R. And second, the R torsion points over Fp to the K are going to be isomorphic to integers modulo R times integers modulo R. Okay, now the terminology. K is called the embedding degree of E with respect to R. With respect to R. Usually in the examples we take, in the examples we take in practice, you choose a curve, what is called, you cannot choose just any curve. You want to choose a curve in which K is reasonably small. Okay, and so there are methods to choose specifically these curves. If you just randomly select a curve, the chances you will get what is called a pairing friendly curve are basically zero, close to zero. But you can engineer it this way that you find still an infinite family of curves that satisfy your various assumptions. Okay, how do we do the pairings? For the pairing, choose G1 to be the R torsion points of E over FP. G2 is going to be a subgroup of the R torsion points over Fp to the K, where K is the embedding degree. Remember, this guy is integers modulo R times integers modulo R. So I need to choose a subgroup of order R inside this guy. the way I do it, I mean, I'm just going to say it. This is going to be, there is a map, the trace map from EF P to the K to EF P to the K. And I take the kernel of the trace. This is the collection of all P such that a trace of P is equal to 0 to O. And G2 is this kernel. And that's G2. GT is simply mu R. The roots of unity mu R of FP. This is the roots of unity R roots of unity inside. This is a theorem. They all fall inside F P to the K for the same K. So this is a theorem that, remember we talked, the roots of unity is the collection of all X such that, or we denoted maybe W such that W to the N is equal to 1. The collection of all W in large enough extension belongs to a large enough extension of FP. So it turns out that for the embedding degree K, the large enough extension in which all the roots of unity of order R live is FP to the K. Okay, and then the theorem essentially by Whale. I mean, of course, cryptographers modified this a little bit for these choices. There exists a pairing E from G1 times G2 to GT. Okay, so to answer the question of what is the multiplication, and now you should understand what is the multiplication in GT is just multiplication in FP to the K. Okay, and the addition in G1 and G2 is just the addition of the elliptic curve group. Okay, so just back to the BLS. Remember, I have a hash function into G1. G1, I know what is G1. G1 is E of F P R torsion. And then the signer chooses a secret key at random from ZR and computes the public key as the secret times the generator of G2. And then, so this guy lives in G2. And then I sign. The way I sign on a message is by computing sigma to be S age of M. And this, of course, is an element in G1. And the way I verify, I apply this pairing on sigma and G2, and I check whether it's equal to the pairing of HM and P to and PK. Okay, but these guys, they live in the group of Rth roots of unity, mu R. This is GT. Okay, security of this thing. Security of this thing relies essentially on the hardness of discrete log in GT. So in order for the discrete log to be hard enough, we want, I mean, GT is a group of size R, but it really lives in FP to the K. Where is it written? Right, this lives in F, just the field FP to the K. And so even if P large enough, I still need, I mean, even if P quite large, let's say 300 bits, I still need K to be around 10 in order for the discrete log in mu R to be hard enough. So what do people do in Ethereum? There are two curves that are currently being used. One of them is, well, let's do the table like this. The equation, field, size, the size of the prime R, the embedding degree, and the security. The bits of security that you get with these parameters, and the two curves, one of them is called BN 254, and the other is BLS 381. It's not, the BLS is acronym for the authors, but it's not the same authors as the BLS signatures. Okay, so what do you get here? You get the equation is, in the first case, is y square equals x cubed plus some b. And in the BLS, it's very nice. It's y square equals x cubed plus 4. This is going to be valid in very, very large family of fields. But the field size you choose in the first case is 254 bit size prime field. And in the second case, you choose a prime field of size 381 bits. The size of R is actually approximately the same size as the size of the field. This is again something that you need to engineer well in order to get a curve with this property, but it's possible to find a curve such that the number of points, the prime that divides the number of points is very large. It's almost of the size of the whole group. So it's going to be 254 bits. And here it's a slightly smaller than the size of the field. The size of R is 254 bits. Sorry, this is 255 according to my. However, and the embedding degree in both cases is 12. However, I forgot. We need to say the size of a p to the k, right? Because or the size of a fp to the k, because we land in fp to the k. Because the size of fp to the k in the first case is about 3048 bits, and the size of the field in the second case is about 4572 bits. Therefore, because the security is mostly the security of the discrete log in fp to the k, you get better security in the second case. So you get here, you get 100-bit security, and here you get 128. Okay, and so BN254, I mean, it is a pairing friendly curve, and it is used in the, BLS 381 is used in the beacon chain, so in the consensus layer of Ethereum, and eventually the plan is to move to BLS 381 for everything because it has better security. What else did I want to say? Yeah, let's stop here. Maybe I'll remember what I wanted to say at the last remark.
Very well. Yeah, thank you so much. We covered the curves. Before we wrap up, then let's have some questions, folks. There was a question earlier. Prabal, if you want to maybe elaborate on that, I'm not sure if it was answered for you meanwhile.
Yeah, so yeah, I see. Prabal. This is what I tried to explain. So the question is, what is the fundamental property of elliptic curves that allows us to achieve the same level of bits of security with a smaller prime? And the fundamental property is that in order to do a discrete log attack, which is kind of brute force, you need to, what is the discrete log? I give you SG1, but I don't tell you what is S. I give you this as an element X. Given X, find S. In order to find S, you will need to do a lot of additions in the elliptic curve. I mean, you have to do a lot of guesses, and your guesses are going to be a generator plus generator, or generator plus generator plus generator. But this is expensive operations because this is G1 plus G2. G1 plus G1 in the elliptic curve. You need to solve some equation, so you need to do the tangent line and then solve the system of two equations in two variables that give you the intersection and then reflect along the x-axis. This is only to do G1 plus G1. So an attacker needs to spend a lot more time on their brute force attack, and that's why, in order to get the same level of security, you can use a smaller prime. And at the end of the day, that's what I said earlier, it becomes more efficient to use elliptic curves groups even without the pairing property. So Diffie-Hellman, I mean, many things in practical cryptography on the web, on your browser and so on, are just elliptic curve based groups because of this property. Other questions?
Folks, do you have any more thoughts, any questions? It's the end of our session, so is the best opportunity to ask something now or the very last one, Lee?
Yeah, thanks a lot. And I have a question from the beginning of this part. Our first observation in this second hour, if AB over FP and K larger than 1, you say here X1 belongs to FP over K, products FP over K. What do you want to say here? I don't get the point.
I said, you see the tablet now? I mean, I said we can speak about the points of E over FP to the K. I mean, E is defined, remember, E is defined over FP originally, right? And so we have the so-called FP points. It's like, just think about it this way. If I had an elliptic curve over R, because R is contained in C, I can talk about the real points, and I can talk about the complex points. The complex points, it's the same equation, right? The equation is defined over the real numbers, but the complex points is the set of x, y in C times C that satisfy this equation, the equation of E. Okay, but now there could be more points in E of C than the points you have in E of R, because C is a larger field. There could be more pairs of points that satisfy this equation. Okay, the same is with a finite field extension. I mean, FP is a subfield of FP to the K. Okay, so any equation over FP makes sense as an equation over FP to the K. So I can talk about the solution to the equation over FP to the K, to the same equation of E. Yeah, the same here in the box, same equation. And this is also a group. Basically the same properties I mean the same constructions we described with like the line connecting the 2 points, intersecting the curve and reflecting, or doing the tangent line and so on. This also gives a structure of a group on EFP to the K. And this group, I mean, an EFP is a subgroup of this bigger group. And it's potentially, it could be that they are equal, but potentially this group is bigger. Is this clear, Lee?
Oh, yes. Thanks a lot.
Okay, so this is the same. We had a similar principle, right? We had like polynomials over FP. They make sense over FP to the K. So I can look at solutions to polynomial. We did it in one variable, and here the polynomial of the elliptic curve is in 2 variables. But the same principle applies. Whenever you have a field extension, one equation over the small field it makes sense over the bigger field. So we have, and that's why I said E over E itself is not just one group, because E over Fp is one group, E over Fp to the k for any k is another group. So you have a family of infinitely many groups. And this is important to know because when we work with the pairing, which of course I did not construct the pairing, this is a long way to go, but I just described what are G1 and G2. So G2 is living in the EFP to the K. Okay, so this is this is not the original group of the curve over FP. It's the group coming from the curve over an extension of the field. Okay, so it's important we use in the pairing we use these observations.
But here actually G2 from the torsion, R torsion, right? Over
Yes,
the extension.
but R torsion of EFP to the K.
Yeah.
Okay, what is EFP to the K? It's like FP to the K is like an extension of FP. It's like a complex numbers extending the real numbers. So you need to know that EFP to the K, just the green thing, is a group in its own right. Okay, and then you can take the torsion points. The torsion points of this guy is the collection of all P in this group, EFP to the K, such that RP is equal to O. Okay, and this is potentially bigger than the collection of all points in EFP, such that RP is 0. You see the point? It's like the torsion. Also, the construction of the torsion depends on which field you take the points over.
Yes, that makes a lot of sense.
Okay. Any last questions? Final famous words? Then, just before we leave, Mario, correct me if I'm wrong or clarify this thing, but I understand that there are some projects that you do it at the end of the day, and I think I should appear in the list of potential advisors. So you're welcome to contact me for this.
Yes, I mean there will be projects for the fellowship later in like next month when the fellowship starts. I will be in touch with you, Matan, about that. And for everyone, of course, like if you want to work on something related in cryptography, I can connect you with Matan if you have any relevant questions or projects you want to work on. And for now, I want to say a huge thanks to you, Matan. I mean, it's been incredible. It's been now 6 weeks journey, 5 lectures, very intense, very real mathematics, and and it's incredible to actually understand the cryptographic protocols behind Ethereum, not just to use it or you use some libraries that just work, but to be able to understand. And I understand for many of you folks, it's been tough to chew through all of the mathematics here, but we have all the recordings, we have all the resources provided by Matan, so you can always do this course in the future at your own pace, and this will live with us for a while. And thank you so much for everyone who've been attending these. We got over 20 people in each of them, so it's been I see all of you been many active. So yeah, thank you so much, everyone, and especially again, Matan. Thank you so much. I've learned a lot myself. Honestly, I am surprised how deep the rabbit hole goes, and it's just the beginning. Of course, we can learn so much more. So thank you so much for taking the time with us every Monday for the last 5 weeks. It's been amazing. Let me switch here.
Yeah,
Yeah,
and,
awesome.
and thank you, Mario, also for coordinating everything and helping out. I enjoyed it as well, so hope we can do it again sometime.
Yes, of course. You are a great teacher, Matan. I appreciate it more than whatever they try to teach me in university. So you should definitely continue with these in one form or another. So thank you so much. Yeah, incredible. And with this, we are closing the cryptography track of the protocol study group. So thank you so much again, everyone. And I hope to see you guys and hope to see you, Matan, around elsewhere. Yeah. Yeah, if you need to get in touch with Matan, yeah, I've showed you his website before, but you can contact me, of course, and I will share you all the resources you need.